BGP, and they do not know about the routes that are coming either from router 7 or from backbone 1. Okay, so router 6 is receiving routes from RIP in from backbone 1. It's redistributing RIP into BGP and advertising them as VPN v4 routes over to router 3. Router 3 is then taking the VPN v4 routes, importing them into the VRF table, and advertising them as RIP routes out to router 7. Okay, so we're performing mutual redistribution between RIP and BGP on both router 6 and router 3. Okay, now, again, if we look at the logic of how the VPN forwarding is going to work, the MPLS VPN forwarding, router 6 is advertising, in addition to the regular prefix, is advertising a VPN label. So router 6 is saying to router 3, in order to get to those routes coming from backbone 1, you're going to use me as the next hop, and you're going to use the MPLS label that I am advertising to you. Previously, what happened is that router 3 already knew an MPLS label, a transport MPLS label, in order to reach the loopback of router 6. Okay, you'll see the terms transport label or IGP label being used interchangeably. Okay, the IGP label, the transport label, that is going to be the topmost label that is being used for switching through the service provider network. The BGP label, or the VPN label, that is going to be the underlying label that router 3 and 6 use to figure out which VRF the final destination traffic is supposed to go to. Okay, because in this case we see there are two VPNs on each of the provider edge routers. We have VPN A and VPN B. When router 6 receives a packet in from router 3, it's going to need to know what is the final destination for that packet. Okay, the reason why is that we could have on VPN B the same route as we do on VPN A. Okay, so what we'll do, after we look through our basic verification, we'll go to router 8, set up this VPN, then we'll configure this 212 network. We'll say 212.100/24. This is going to be an identical prefix that backbone 1 has. But since they are in separate VPNs and have separate VPN labels, router 6 is going to know which interface it needs to send it out. Is it going to send it out the interface to router 8, or is it going to send it out the interface to backbone 1? Okay, so the traffic flow, what's going to happen here is router 7 is sending a packet into router 3 that its final destination is over on backbone 1. Okay, the packet is coming in, the final destination is backbone 1. Router 3 is going to do a lookup, and it says, I know this from BGP, I know it from router 6. Since router 6 is reachable through a label switch path, I am going to impose not only the VPN label that router 6 was advertising to me, but the IGP label or the transport label in order to reach the loopback of router 6. So when router 1 and router 5 receive the packet, they are going to be switching on the outer transport label. They're saying, move this traffic towards router 6. Once it gets to router 6, it's router 6's responsibility to figure out what is the final destination. Okay, so let's look at this on the command line. Let's look at this on the command line, and we can see specifically how this label distribution process works and how they're choosing which labels are going to be used when they're actually switching the packets. Okay, now, from router 7's perspective, this is just a regular IP version 4 packet that is being sent out the interface. Okay, it says the destination is 212.18.01. We're sending it out towards router 3. When router 3 receives it, it is received inside an interface that is in VPN A. Okay, it comes in an interface that's in VPN A. So what router 3 says, look in my VRF table for VPN A. Do I have a route for 212.18.0.1? We see we do have that route. It's known via BGP. And we see the next hop for the route is 150.1.6.6. When we do a lookup on 150.1.6.6, we see this is not actually in the VPN table. It's in the global routing table. It's inside the global routing table. So router 3 is actually going to be doing two separate lookups here. It's doing the lookup on the VPN route. Then it's going to do a global lookup on router 6's loopback. Okay, now if we look at the output from the show MPLS forwarding table, what we see here is that we see not only our IGP labels, for example, we see the label for router 6, router 6's loopback, we also see routes that are tagged as VPN labels. Okay, these are routes that are learned in interfaces running the VRF. Okay, so for example, we have the loopback interface of router 7. It says when we send this out, we're going to send it out untagged, out Ethernet 0/0. Now, depending on the specific version of iOS you're running and the specific platform, this show output is going to look a little bit different. It may or may not show you your VPN labels. Okay, what we need to look at first off, before we look at the forwarding table in our lookup, router 3 is looking in the BGP table, the VPN BGP table, to figure out what is the label lookup for the final destination, which is that 212 network. So on router 3, we need to say show IP BGP VPN v4 all labels. Okay, so we can see inside of the VRF table, we have specific labels that are used for these individual VPN destinations. It says if we're trying to get to the network 212.18.0.0, it is reachable via router 6. The incoming label is none because it's coming from our customer-facing interface. Okay, they are not running MPLS, so it's going to come in as a regular IPv4 packet. We are going to impose the VPN label 29. It is going towards router 6. Okay, so first thing we're going to do, we're going to impose 29. Now we need to look at what is the label going towards router 6. This is going to be inside the global table. So we need to now say, show MPLS forwarding table. How do we get to 150.1.6.6? It says this is reachable out serial 001/2 via the outgoing tag 19. So this packet is first going to be taken in as IPv4. It's going to be labeled with 29. A label 29 is going to be pushed or imposed onto the IPv4 packet. Then we are going to impose the IGP label of 19. Okay, so when someone receives this packet, they're going to see a label of 19. They're going to see a label of 29. Then they're going to see the actual IPv4 packet. And now we can verify this if we go over to router 1, who's the next hop in the path, and we're going to say debug MPLS packets. Okay, so we'll go ahead and log this to the buffer. We'll say no logging console. Clear the log, and then debug MPLS packets. Okay, so from router 7, we'll go ahead and send this traffic. Okay, we see that we do have reachability. Now, if we take a look at router 1 and say show log, what we see here is that inbound on serial 2/1, we received an MPLS label stack. The first label is 19. It has an MPLS experimental value of 0. The time to live is 254. There is another label of 29. The experimental bit is 0. Experimental value is 0. Time to live is 254. Inside that label stack is IP version 4 traffic. When router 1 is switching this, it is only switching based on the outer label 19. So when we say show MPLS forwarding table, what we need to look at is what is the, when a label comes in as 19, what are we going to do with it? It says if a label comes in as 19, we're going to swap it with 17. We're going to send it out fast Ethernet 1/0 towards router 5. Okay, so if we go to router 5 now, and we do the same thing, we'll say logging buffered, no logging console. We'll clear the log, and we'll debug MPLS packets. We can see the output here looks a little bit different in the debug. Router 1 is a 7200 running 12.2S. Router 5 is a 3640 running 12.3T. Okay, so between the service provider trains and the regular enterprise trains, there's a little bit different in the debug and the show output. Okay, but what we see here is Ethernet 0/0. This is the interface coming from router 1. Okay, we received an MPLS stack. The time to live is 253. So it was decremented once. It was decremented by router 1. MPLS experimental value is 0. The first label is 17. The VPN label is 29. Okay, so if we scroll back up to router 3's output, we can see 29 is the original label that router 3 is imposing. This is the VPN label. When this packet reaches router 5, label 29 is not been modified. Okay, this is the label that is at the bottom of the stack, 29. Okay, so when we look at router 5, we can see it came in as 17. It also has a label 29 underneath it. Now it came in as 17 because when we looked at router 1's forwarding table, router 1 said if it came in as 19, swap it with 17, send it out to router 5. So router 5 is receiving it with 17, and underneath that is the VPN label. Okay, if we look at router 5's forwarding table, we show MPLS forwarding table. It says that if a label came in with the tag 17, remove the topmost label, send it out to router 6. Okay, so if we look at router 6 now, we'll say no logging console, log to the buffer, and then we'll send the traffic from router 7 again. And if we look at router 6's log, it says we received a label packet coming in gigabit 00. The label was 29. We're sending it out serial 0/0/0. This is out to backbone 1. We're sending it as an unlabeled IP version 4 packet. Now, if we look at the forwarding table of router 6, show MPLS forwarding table, we can see it says that if a packet came in with label 29, this is a VPN packet. We should send it untagged, so we should send it as a regular IP version 4 packet out serial 0/0/0 towards 54.1.1.254. Okay, so we have a question here. It says label 29 is assigned by router 6. Correct. Okay, so router 6, as it is populating its VPN table, it's saying, I am assigning label 29. Okay, because from the perspective of the MPLS VPN network, router 6 is the highest downstream device. It is closest to the destination. It is closest to the destination. So router 6 is telling router 3, if you're sending traffic to this destination, use label 29, because this is what I have installed locally in my forwarding table. So it's saying use the label 29 use the next hop 150.1.6.6, which is my BGP next hop value. Now, as long as everyone in the transit path can reach 150.1.6.6, they are going to be able to get the traffic to me. Once I receive it, I'm going to look at what the VPN label is. We see that it is a VPN packet, and that goes out serial 0/0/0. Now, if we look in the transit path, if we go to router 1 and say show IP route, we can see that router 1 does not have any information about the 204 or the 212 network. It does not have any information about the 212 network. It only has information about router 6's loopback and router 3's loopback. There's a question here, what's the difference between untagged and aggregate? If we scroll back up and look at router 6, the aggregate labels, these are the ones that are directly connected. Okay, the loopback 10.1.6.6, this is directly connected, and the 54 network is directly connected as well. Now, if we look at the process on the way back, if we look at router 3 and say show IP route 10.1.7.7, we see this is not in the global table. It's in VPN A's table. It's in VPN A's table. If we look at the MPLS forwarding table, we see router 3 has assigned that if someone is going to 10.1.7.0, they're going to use label 23. Okay, that's the incoming label that I want to use. So if we go over to router 6 and say show IP BGP VPN v4 all 10.1.7.0, we're looking at this specific prefix. We can see that the outgoing MPLS label should be 23. So if we correlate this with what router 3 said, router 3 assigned 23 because it is closest to the destination. Okay, so router 3 is assigning the tag, then it is propagating it into the rest of the network. Router 6 has to use whatever label assignment that router 3 is determining. If router 6 turns around and passes this to someone else, it's going to be whatever local incoming label that router 6 says will determine what the other devices should use. Okay, so if we debug this on the way back, actually if we let's look at router 1's log. You can see as the traffic is going back to the source, the VPN label is 23. Okay, this was the label that router 3 assigned and propagated it through VPN v4 BGP over to router 6. Okay, there's a question here. Is there a show command that is used on the P routers to verify that the VPN label is assigned? Okay, the only way on the P routers, router 1 is a P router, the only way that we can see what the VPN label is by looking at the debug output. A router 1 does not assign these VPN labels, nor does it have it installed in the forwarding table. Okay, we can see we actually are reusing that label number that is inside the VPN stack. Router 3 is assigned 23 as a VPN label. Router 1 has assigned 23 as an IGP label. if we show MPLS forwarding table, we see 23 is supposed to go out to router 3. If router 3 were to receive a packet with 23, it would say this is going to 10.1.7.0. Okay, so in this manner, we can see that the labels are locally significant. They can be reused in the network. But when router 1 receives this traffic, it is only looking at the first label in the stack. Okay, so the topmost label in the stack, this is what it's making its forwarding decision based on. Okay, so let's go ahead and we'll add VPN-B into the mix. And we'll see what happens when we have multiple VRFs on the devices and how they're distinguishing between multiple possible destinations. Okay, so we're going to configure VPN-B on both router 3 and router 6. This is going to connect to backbone 3 and to router 8. Okay, so let's go over to router 3 and we're going to define this new, we'll define the new VRF here. Okay, so we'll say IPVRF, this is going to be VPN-B. We'll say the route distinguisher is 150.1.3.3:2. So this is our second VPN instance that is being advertised by router 3. We'll say the route target is 102. Okay, so previously we had 150.1.3.3:1 as the route distinguisher, and the route target was 100:1. Okay, so we need to make sure both the route distinguisher and the route target is unique. Okay, we'll show in a little bit here what happens if the route targets are overlapping. What is going to happen between? What is going to happen with the traffic? Okay, so first off, we define the VRF. We'll do this on router 6 as well. IPVRF VPN-B. Okay, and now the name of the VRF again is only locally significant. So the name of the VRF is only for assigning it to the interface. It's the route distinguisher and the route target that is going to control where the traffic is, where the networks are being advertised to, and what tables they can be installed in. Okay, so we're defining the route distinguisher. Now we're going to define the route target. And now on the interfaces, we'll go ahead and enable the VRF. So this is going to be on gigabit 01. We'll say IPVRF forwarding VPN-B. Okay, this is going to remove our IP address, so we need to go ahead and reassign that. And we'll do the same thing on router 3. Okay, so on Ethernet 01, we'll say IPVRF forwarding VPN-B. Reassign our IP address. Okay, then we'll test basic connectivity between the PE and the CE before we move on to any of our routing configuration. Okay, we'll say ping VRF VPN-B. And backbone 3 is going to be 204.12.1.254. Okay, so we have reachability between router 3 and backbone 3. Then on router 6, we should have reachability to 10.1.68.8. And now we'll go ahead and define our PE to CE routing instances. Okay, and in this case, we'll use RIP version 2 for both of these links as well. So on router 8, we'll say router RIP, version 2, no auto summary, network 10.0.0.0. Now on router 6, this is going to be a VRF instance for RIP. So under RIP, we'll say for the address family, IPv4 VRF VPN B instance, we want the same options there. As a quick side note here, in Secure SIRT, if you hold down Alt and then select, you can do column mode. Okay, so the same configuration on router 6, but this is going to be in the VRF instance. So if we say on router 6 now, show IP route VRF VPN B, we see we have that RIP route coming from router 8. Okay, router 3, we're going to do the same thing. So under RIP, address family IPv4 VRF VPN B, we're running RIP version 2, disabling auto summary, and this is going to be 204.12.1.0 is the network we want to run it on. Okay, so we can see just like the regular show IP route output, we can filter this through specific protocols. So we're saying just show us the RIP routes that are in VRF VPN-B. You can see we're learning all these prefixes from Backbone 3. So at this point on router 3, we should be able to ping inside VRF VPN-B to any of these routes. We'll say 30.0.0.1, for example. Now, if we look in the MPLS forwarding table, what we should see actually, we don't have the BGP instances defined for it yet, so we're not going to see it. But once we go ahead and enable this VRF instance inside multi-protocol BGP, we're going to see that router 3 is going to provide VPN tags for all of these IGP learned routes. Okay, so we have the IGP routes learned from the provider edge. We have the MPLS core built. We already have our multi-protocol BGP peering between them. So the only thing that we need to do is advertise these RIP routes from VPN-B into multi-protocol BGP. So under our BGP process, we'll say address family IPv4 VRF VPN-B. We want to redistribute RIP, and under RIP, we'll say redistribute BGP 100. Okay, now this configuration is going to be identical for VPN-B and VPN-A. So we're saying redistribute RIP and then redistribute BGP 100 metric 1. Okay, now the routes that are being chosen for redistribution are based on what is installed in the VRF table and based on the route target. Okay, it's going to be based on the import and the export route target. So what is going from RIP into BGP, that is based on the export route target. What is going from BGP into RIP, that is based on the import route target. So we're importing it into the VRF, or we're exporting it out of the VRF into BGP. Okay, so the route target, keep in mind, it's always from the perspective of the VRF. Okay, then we're going to do the same thing here on router 6. So under BGP, we have this address family. We're going to redistribute RIP routes in there. Then under RIP, for this address family, we're going to redistribute BGP. Okay, so once we configure this, we want to verify it by looking at the BGP table and see first off what routes came from the VRF locally and were exported into BGP. So we could say show IPBGP VPN v4 route distinguisher 150.1.3.3:2. Okay, what this is going to show us is just the routes that router 3 has taken from VPN-B and put into BGP. Okay, we can see that we have all these 30 networks. We can see this is the default route distinguisher for VPN-B. We can also see that we have routes coming from router 6. Okay, the reason why these are in there, because the route target for these prefixes, if we say, do the same show command, and then we'll say show 10.1.8.0. Okay, that prefix there had a route target of 100:2, which is the import route target on router 3. So we are importing this from BGP into the VRF. It would not show up in this VRF table if it did not have a matching route target that we were importing. Okay, so if we look at the same thing on router 6, show IPBGP VPN v4, look specifically at our route distinguisher for this VPN. Okay, we see we have our own routes, plus we have the routes coming from IGP. Okay, so if we go to router 3 here, and we say show MPLS forwarding table, what we should see is that for each of these IGP routes that are coming from the CE neighbors, we have corresponding entries for them in the MPLS forwarding table. Okay, so router 3 is saying that if anyone wants to get to these 30 or 31 networks, these are the MPLS labels that they must use. Now we can correlate this, let's say the 30.0.0/16 network. It says use label 31. If we go over to router 6 and say show IP BGP VPN v4, we'll say it doesn't matter what the route distinguisher is. We'll say look at the prefix 30.0.0.0 with a mask of 255.255.0.0. Okay, so specifically 30.0.0/16. We can see this has an outgoing label of 31. This was the label that router 3 assigned as its incoming label. Okay, so if we look at the forwarding table again on router 3, we can see that for all of these VPN routes, all of these local labels are unique. So even if we were to have the same prefix, it would have a different incoming VPN label, so router 3 would know where to send the traffic. Okay, so if we go over to router 8 here and we look at the routing table, show IP route rip, we see we have all these 30 and 31 networks installed as RIP routes. Okay, they're learned from router 6. So when we go to reach these, so we have those installed, but we don't have connectivity to it. Let's source this from 10.1.8.8. Okay, now when you're doing your testing of connectivity in the MPLS VPN, you have to be aware of where you are sourcing the traffic from. Okay, with the service provider networks, you'll see that a lot of prefixes are not going to be advertised into either BGP or IGP. So for example, the transit networks within the service provider network, there would be no reason to advertise those to the internet. You know, a service provider does not want people on the internet sending traffic to their transit links between routers. Okay, so traffic should never go to the link, it should always be transiting through the link. And MPLS is allowing it to transit through the link. Okay, so in this case, we see even when we're sourcing it from this loopback here, we do not have connectivity. Okay, so first thing we want to check is the route being propagated to the final destination. Okay, before we look at our MPLS troubleshooting, we want to look at just our basic IGP reachability. So when we look at router 3, is this installed in the VRF? We'll say show IP route VRF VPNB. Okay, we do have 10.1.8.0 learned via router 6. Okay, so that is installed properly. Now let's go over to backbone 3 and see if it has that route installed through RIP. Okay, backbone 3 does not have the route via RIP. Now in the CCI lab exam, it's unlikely that you're going to be able to get access to E or CE devices, the backbone routers, in order to do this type of troubleshooting. So what we'll do, let's look at this from the perspective of router 6. Or actually, the perspective of router 3, who is the attached PE router. Okay, what we could tell to see if this is getting advertised, we'll look at the RIP database. Say show IP RIP VRF VPNB, or just show IP RIP database. Show IP RIP database for VRF VPNB. Okay, we do not see those routes being advertised into RIP. Okay, we should see them via redistributed. So it means that router 3, for some reason, is not advertising them into the RIP database. Okay, so let's take a look at the running configuration here. Show run begin router RIP. Okay, so what I did here when I was doing the redistribution, I redistributed BGP 100 into the global RIP table. Okay, this is saying redistribute global BGP into the global RIP table, into the regular IP routing table. In our case, we want it to be specifically for VPNB. Okay, so we need to move this to under the address family. So under RIP, no redistribute BGP 100. We'll say address family IPv4 VRF VPN B. Redistribute BGP 100 metric 1. Okay, so now if we look at the RIP database, we see these routes via redistributed. Okay, that's what we should see. Then if we look at backbone 3, let's take a look at backbone 3's config. It may be filtering these updates out. Show run, begin, router, RIP. Oh, that's why. This is configured for VRF Lite, and I'm looking at the wrong routing table. That's why. So we should say show IP route VRF DB31 RIP. Okay, so it does have those RIP routes. Okay, so from router 8, we now have connectivity. Okay, so if we look at the hop-by-hop process again, we go to router 6, we see we received a packet that came in to 30.0.0.1. Okay, we see it was received on an interface that is participating in VRF VPNB. So router 6 is going to say show IP route VRF VPNB. How do we get to 30.0.0.1? Okay, we know this destination via BGP The next hop is router 3's loopback. Okay, router 3's loopback is in the global routing table. It's telling us here it's in the default routing table, the global table. If we look at the global table, show IP route 150.1.3.3, this is reachable via router 5 out an interface that is running MPLS. So this traffic is going to be MPLS labeled. Okay, so we can see what the transport label is if we say show MPLS forwarding table for 150.1.3.3. 19 is our transport label. And if we say show IP BGP VPN v4 all labels, we see that our VPN label should be 31. Okay, so when we look at the debug output on router 5 of the debug MPLS packet, what we should see is that we have a transport label of 19. So the first label on the stack is going to be 19, then the underlying VPN label is going to be 31. Okay, so we can see a packet is received inbound, MPLS packet received inbound on Ethernet 0/1. The MPLS experimental value is 0, time to live is 254, the transport label is 19, and the VPN label is 31. So based on this, we can see it's coming from router 6, it's going to router 3, but the final destination is actually that 30.0.0.0/16 network, and that's based on the VPN label. Now, from router 5's perspective, it does not know anything about the VPN label. Okay, this is an inherent security mechanism that is built into MPLS by the fact that no one can spoof traffic going into VPN-B now because they don't know what the final destinations are. Okay, they don't know how to build these labels because on router 5, if we said, how do we get to 30.0.0.1, we don't have that route. Okay, we don't have it via BGP. We're actually not even running BGP in this case. And we don't have it via IGP because IGP is only used to distribute the internal routing information through the service provider core. Okay, any questions so far about the two basic MPLS VPNs that we set up here? Okay, there's a question here about the issue that we were running into before with router 6 not receiving the routes from router 3. It was because router 3 was trying to negotiate IPv4 unicast along with VPN v4, and router 6 was configured only to accept VPN v4. Okay, so whenever you're running BGP with a neighbor, you need to make sure that they are running the same address families with you. Okay, so if one neighbor says, I want to run IP version 4 and IP version 6, and you say, I'm only going to run IP version 6, then you're going to have some problems in exchanging the updates. Okay, you will see the adjacency form in the show IP BGP output, but you'll see some inconsistencies like we saw where the routes were being advertised, but they were not being installed in the table. Okay, there's a question. How does the forwarding take place? Are you referring to the forwarding on router 1? Or okay, let's take a look. Since it doesn't have any routes. So how does the forwarding take place on router 1 since it doesn't have any routes? Okay, let's look back at the logic of how the imposition process works. Okay, first off, inside, actually there's a step before this. Okay, this is assuming that we have IGP running inside of the service provider network. Okay, so between routers 1, 3, 5, and 6 here, in this case we're running IS to IS. Okay, IS to IS. We could also be running OSPF. Okay, so our IGP is built. Router 3 is advertising its loopback into IGP. Router 6 is advertising its loopback into IGP. Okay, then we are running a label distribution protocol between them. Okay, with IGP, we could either be running LDP or we could be running TDP. Okay, Brian Dennis is going to show later some examples of how you can just avoid those protocols completely and run RSVP to do label distribution based on traffic engineering. Okay, but the LDP and TDP configuration, typically you'll see most networks routed via LDP because the configuration is very straightforward. You just enable it on the interface and it automatically detects neighbors that are adjacent to you. Okay, with mechanisms like BGP label distribution, which we'll take a look at tomorrow, and RSVP label distribution, you need to manually specify who you are distributing the labels to. And as the service provider network grows, you have that scalability problem of the full mesh. Okay, so if you have 100 different provider edge routers, you would have to have tons of different tunnels set up between them to distribute labels. Okay, but in this case, we're running IS to IS in the interface, then we're running TDP. If we could switch it over to LDP, and it would accomplish the same exact thing. Okay, now router 6 is saying to router 3, if you want to reach my loopback, router 6 is saying to router 5, if you want to reach my loopback, send me an unlabeled packet. So I am advertising implicit null. Okay, this is causing router 5 to perform the penultimate popping process. So router 5 is saying, if I have a packet coming in towards router 6 loopback, I'm going to remove whatever the top label is in the MPLS stack, and I'm going to forward it on to router 6. Okay, now there's a difference when we look at the table. There's a difference between the pop tag output and the untagged output. The pop tag means remove whatever the topmost label is in the MPLS stack. The untagged output means remove the entire MPLS stack and send it as a regular unlabeled IPv4 packet. If you see the unlabeled output between the neighbors, it means that they are not properly negotiating label distribution. Okay, let's take a look at that on the command line here quickly. And we'll take a look at this in more detail on Friday. We'll take a look at this in more detail on Friday when we go through troubleshooting. Okay, one of the problems that you could have is, let's say that Ceph is not enabled. The MPLS label distribution is dependent on Cisco Express forwarding being enabled. Okay, you cannot run MPLS without Ceph being enabled. If we look at router 1 now, who is adjacent to router 5, and we say show MPLS forwarding table, we can see that we are learning these prefixes. We have them installed in the forwarding table, but as we are sending them out to router 5, we are not sending them as labeled packets. Okay, this is an error in the label negotiation, the label distribution. Since router 5 does not have Ceph enabled, it is not binding labels for these destinations. Okay, we should not see this no label output. We should either say pop label, untagged, or a regular value that we have installed. Okay, when it says no label, it means that we did not properly negotiate a label for that packet. It means we're going to send it as a regular IPv4 packet. Okay, once Ceph is re-enabled on router 5, look at back on router 1, show MPLS forwarding table, we see we have a regular label value here for going to router 6, and we are doing 10 ultimate hop popping for these destinations, for router 5's loopback and the connection between router 5 and router 6. Okay, so this is the first step in the network. We have our IGP, then we have our label distribution mechanism built. So now we have transport between router 3 and router 6's loopback. Okay, this process is going to happen the same way, opposite from 3 to 6. 3 is going to advertise implicit null to router 1. Router 1 should advertise a regular label value to router 5. 5 is going to advertise a regular label value to router 6. Okay, the next step, we have the routing advertisements. This is going to be the routing advertisements from the CE to the PE. Okay, in this case, backbone 1 is advertising network X to router 6. Okay, how it is advertising it doesn't matter. It could be router 6 could have a static route. Backbone 1 could be sending a BGP route. It could be via IGP. In the specific case that we looked at, we were using RIP as the PE to CE protocol between router 6 and backbone 1. Okay, so router 6 takes this update in from from backbone 1, takes the update from backbone 1, and it sends it into BGP to be advertised over to router 3. The type of route, as it is advertised from 6 to 3, is going to be a VPN version 4 route. Okay, this is a VPN v4 route. What this means is that it's going to be the route distinguisher followed by the prefix, and it's also going to be the MPLS label. So router 6 is saying, this is the route distinguisher, this is the IPv4 prefix. That makes sure that the prefix is unique. Okay, then it is also sending it a label binding. That is going to be the VPN label that router 6 wants router 3 to use when it is forwarding the traffic. Okay, so now router 3 knows its 3 pieces of information it needs. It knows the route to the destination, it knows the VPN label for the destination, and it knows the IGP label in order to get to the next hop. So the IGP label to the next hop is going to be towards router 6. The VPN label is going to be towards the final destination, which is network X in this case. Okay, then the traffic flow, router 6 receives, or router 3 in this case, router 3 receives an untagged packet from router 7. It imposes the VPN label, V1. Then it imposes the IGP label, L2. This IGP label L2 says to go to router 6. The VPN label says to go to network X, the final destination. When router 1 receives it, it is looking at just the topmost label in the stack. It's looking at label 2. And since router 1 knows to use label 2 to get to router 6, it can swap the label and send it out to router 5. So from the perspective of router 1, it is looking at just the topmost label in the stack. Okay, so let's take a look at router 1 here. We look at the forwarding table, we see it has the entries for router 6 and it has entry for router 3. Okay, let's go to router 7 and let's look at one of these routes. Show IP route RIP. Let's say we're going to send traffic to 212.18.01. Okay, we're going to send it as a high repeat count. So we're going to keep pinging this destination. Now, if we look at router 1 in the MPLS forwarding table, what we're going to see is that the counters towards 151.66 and 151.3.3 are going to be going up and up. So say show MPLS forwarding table and include just these two entries. So what this is implying here is that when router 1 receives this traffic, it's seeing two different things. As it's going from router 3 to router 6, it's seeing it as label 19. As it's going from router 6 to router 3, it's seeing it as label 23. It's performing the PHP process as it's going out to router 3. It's taking the topmost label off. As it's going out to router 6, which is reachable through router 5, it's taking the incoming label 19 and swapping it with the outgoing label 16. Now, when you're troubleshooting your network, especially when we get into some more complex things like inter-AS MPLS VPNs, it's really key to understand exactly how this lookup process works and how to verify this on a hop-by-hop basis. Okay, when you're looking at the PE routers again, you need to look at what is both the BGP label, which is our VPN label, and what is the IGP label, which is our transport label. To look at the VPN label, we say show IPBGP VPN before all labels, or we could say for a specific route distinguisher or for a specific VRF. Okay, so these are going to be the packets that are coming from our customer edge. They're going to these destinations. Okay, these are the routes that the customer edge is trying to reach. As these are coming in, they're coming in as unlabeled packets from the customer. Okay, when we look at advanced configurations like carrier supporting carrier and hierarchical VPNs, MPLS VPNs, we can see that the customers can also be using MPLS labels inside their network. Okay, but in this case, the customer is just running regular IP version 4. So when these labels come in, or when these packets come in, they're not labeled. So we're taking them as unlabeled. We are imposing the VPN label. We can see what the next hop is. Now we look at what is the label we use to reach this next hop. This is a very important process, especially when we get to inter-AS MPLS VPNs. If this next hop is not correct, we can see it being forwarded with the wrong label to the wrong portion of the network, and we can end up with it being black holed. There's a question here. The VPN labels are assigned by BGP and also distributed in BGP updates. Correct. Okay, it's being assigned by the BGP process, and it's being advertised through the VPN v4 update. Okay, one of the good documents on this actually is the standard that it's based on. And let me see, this is listed in here somewhere. Okay, it's RFC 4364, BGP MPLS IP Virtual Private Networks. Okay, it talks about how the route distinguisher is used to advertise the route as unique, and it talks about the label distribution process. Okay, so if you want to get a lot more detailed information about it, then you take a look at that RFC. It has a lot of good information on it. Okay, so if we look back at the command line here, you see that these are the labels that are being assigned via BGP. And when we go to the other end of the network, when we go to router 3, this label 27 should have been defined as an IGP label in the VPN process. So when we look at router 3, show MPLS forwarding table, include 31100, we can see this is using label 27. So router 3 is assigning label 27, advertising it over to router 6, telling router 6 to use label 27 as the VPN label. Okay, so that's the first step that router 6 needs to know. What is the VPN label? Okay, that's assigned via BGP. Now it needs to know what is the transport label. Transport label can be assigned 3 different methods. It can be either LDP and TDP, RSVP, or BGP. Okay, in this case, we're looking at just IGP assigned, which is our TDP protocol or our LDP protocol. So what we're going to look at here is show MPLS forwarding table. What is the label associated with 150.1.3.3? We see that label is 17. So when we build the label stack, it's going to say 17 is the topmost label, then was the route we were looking at. Okay, the 31. 17 is going to be our IGP label. 27 is going to be our VPN label. Then we're going to have the payload, which is going to 31.100. So when we look at our debug output in the transit path, we should see everyone is seeing the VPN label as 27. This should not change. The final destination, or the final provider edge router, I should say, which is router 3, when it receives this packet, it must be receiving it incoming with a label of 27. If this label is removed prior to reaching router 3, the label switch path is not going to be end-to-end. And one of the reasons why that could happen is if you're not peering with the correct BGP address, or you have some problem with your IGP routing in the transit path. Okay, we looked at yesterday a situation where router 3 and router 6 were peering via their Ethernet interfaces, or their outgoing interfaces towards the service provider network instead of peering with their loopbacks. If they were not peering with their loopbacks, then when the traffic got to router 1, on its way to router 3, router 1 would see the VPN label. Okay, router 1 should never see the VPN label under any circumstance. Okay, let's look back at the diagram. In this case, the traffic flow is going from router 7 over to backbone 1. When the traffic reaches router 5 must see the IGP label. If router 5 sees the VPN label, it is not going to be able to do a lookup on it. Or it may do a lookup on it and send it out the wrong interface. Because when we looked at router 1, we saw router 1 was assigning the same label that someone else was using as a VPN label. Okay, but if router 1 or router 5 in this case, which are the P routers, if they see the VPN label, the label switch path is not going to be end-to-end. They have to be switching on the outer transport label. Okay, so when we look at traffic in the transit path for this specific destination, everyone should see the VPN label as 27. This should not be changing. Okay, what will change is the IGP label, the transport label. So when 6 sends it to 5, it's going to be 17. When 5 receives it, it's going to say show MPLS forwarding table. What do I do if I receive a label 17? I'm going to swap it with 23. I'm going to send it out Ethernet 0/0 towards router 1. Router 1 says, I just received an MPLS label that was 23. I'm going to take the top label off of the stack, send it out serial 2/1 over to router 3. When router 3 receives this, now it is going to see just the VPN label. And when router 3 does the lookup, it says show MPLS forwarding table, include 27, it sees this is towards the VPN destination 31.100. Okay, so if you see problems in reachability, this is what you need to do on a hop-by-hop basis. You need to look at what is the VPN label being assigned, that is going to be assigned by the PE router that is closest to the destination. A router 3 is the PE router closest to the 31 network here. It is assigning the VPN label. The IGP label is going to be assigned by either LDP or TDP. Okay, so you look at the show MPLS forwarding table for whatever your BGP peering destination is. Okay, there's a couple more topics we need to cover in MPLS, some of the more advanced VPN scenarios. Do you guys want to break for lunch now, or should we continue for like an hour or so and then? All right, let's go ahead and break now. We'll start back at noon Pacific time. Then we'll look at a few more scenarios with VPNs, and then we'll start talking about MPLS traffic engineering. Okay, the next thing we're going to talk about. Excuse me. The next thing we're going to talk about here this afternoon is some more complex topologies in MPLS VPNs and how we can use route target filtering and specific route target setting in order to build some of these more complex topologies. Now, the one that we looked at so far, we have two VPNs, one running between router 7 and backbone 1, and a second VPN that is running between router 8 and backbone 3. Now, the way that the routes are controlled between the different VRFs is based on the BGP route target. And again, the route target is an extended community in BGP that uses either the AS number followed by colon and a locally significant number, or an IP address colon and then followed by a locally significant number. Okay, so generally, this value, the route target, is only going to be locally significant to the autonomous system. Okay, we are going to look at some situations with inter-AS MPLS VPNs that it can be significant between different providers, but commonly it is only going to be locally significant within an individual service provider. Okay, we still need to make sure that the route distinguisher is going to be unique, because everywhere in the MPLS network that is going to be controlling that an individual VPN v4 route is unique. Okay, so even if we have overlapping addressing, the route distinguisher is going to take care of that for us. Okay, now again, there's two different ways that we can apply the route target. We have an import route target and we have an export route target. The export route target is controlling what is going from the VRF table into the BGP table. So we're exporting the prefixes out of the VRF table. The import route target is controlling what routes we are taking from BGP and importing them back into the VRF. Now, since the route target is an extended community, we can put more than one route target on a specific prefix. Okay, so when we look at the show output, we'll see that there's just multiple route targets listed depending on how we are setting the values. Okay, the way we're going to do this, setting multiple route targets, is with an import map or an export map to control, based on a number of different attributes, what the import policy is going to be and what the export policy is going to be. And now a couple different common designs we have. In the case that we were looking at previously, we had a full mesh where the individual sites within a VPN can talk to all sites within that VPN. So if we added a third site to VPN B, for example, if that third site was exporting the route target that the other sites were importing and was importing what the other sites were exporting, we would have a full mesh of connectivity. Okay, that's where the import policy and the export policy is going to be the same everywhere. Okay, we can also have a hub and spoke design where the spokes are only importing the routes from the hub. So at the spoke 1, we could export routes with route target 1. At spoke 2, we could export routes with route target 2. Okay, the hub would be importing both of those and exporting a different value, for example, route target 3, that both of the spokes would be importing. Okay, so depending on how we want our traffic flow to go through the MPLS domain, we can control this with the route targets. Okay, one of the applications of a hub and spoke would be if we wanted a central point for internet access through the MPLS network for a particular customer, or if we wanted all traffic to flow through a central firewall that was at the hub site. So we could force the traffic from the spokes up to the hub, make it go through the firewall before it goes back to the other spokes to do some type of whatever administrative filtering that we want to accomplish. Another common design is known as central services, where there is a site that multiple VPNs want to access at the same time. So for example, in addition to providing transparent layer 3 transit over the service provider network, the service provider is offering a central server or central service to its MPLS VPN customers. So maybe it could be a file server, maybe it could be a video server. So multiple VRFs are going to be accessing it, but the individual VRFs cannot access each other. Another application of using route targets could be for management VPNs, where in addition to the transparent layer 3 transit, the service provider is also going to be responsible for controlling and managing the customer edge equipment. Okay, now since the customers may be using overlapping addressing, for example, the customers are all using the 10 network. Okay, what we can do is assign a unique address onto the customer edge equipment, then export it from the VRF into BGP with a specific route target that is then going to be imported at the central management location. So we could say that only the management station has access to a specific loopback on the customer edge routers, and the individual customer edge routers do not have access to anything else. Okay, so first thing we're going to take a look at here is how the central services VPN would work. Okay, so what we have here on router 1, we have some central service, let's say it's a file server, that both VPN B and VPN A want to access. Okay, now we already have the policy set up where VPN A is using the route target 101, and then VPN B is using the route target 102. Okay, so what we can do, we can use the route targets that they are already assigned, 101 and 102, to get them access to the VPN central services, or we could define a new route target value on router 1, export that, and then configure an additional import policy on router 3 and router 6. And now, in order for this to happen, this is assuming that router 1 is also going to be running multi-protocol BGP with these devices. Okay, so in addition to the BGP peering between router 3 and router 6 here, we're going to go ahead and add an additional peering, a VPN version 4 peering with router 1. Now, if we can build an end-to-end label switch path with router 1, then we will be able to have transit to destinations located on it. Okay, so let's go ahead and take a look at the command line. And first off, we'll go ahead and set up our BGP peerings and see if the routes within these VRFs are being exchanged between the neighbors. So on router 1 here, let's go ahead and initialize the BGP process. And we're not going to exchange IP version 4 unicast routes with these neighbors. So instead of manually deactivating the individual neighbors, globally under the BGP process, we're going to say no BGP default IP version 4 unicast. If we wanted to go back and enable unicast BGP routing with a particular neighbor, we could go under the IP version 4 address family and then manually activate that. Okay, but in this case, when we issue the neighbor statement, it's not going to apply to any address family. We're just going to establish basic BGP connectivity. Okay, so we're going to peer here with router 3. We're going to source these packets from our loopback interface. And we're also going to peer with router 6. Okay, now we don't necessarily need to source these from our loopback address. We just need to make sure when we're building the BGP peering that we're sourcing it from a link that is not going to cause the PHP process to move one hop downstream in the network. Okay, so we want to make sure that the PHP process does not happen too soon so that the next adjacent neighbor is going to have the correct label packet. Okay, so in this case, we want to make sure that router 5 still does not see the VPN labels. We need to make sure that router 5 is only seeing the IGP labels. And the reason why is because router 5 only has those IS to IS routes. It does not have the BGP routes that router 3 and 6 are advertising via VPN version 4. Okay, so now under the VPN v4 address family, we'll say address family VPN v4. We want to activate router 3. And we want to activate router 6. Okay, then back on router 3 and 6, we're going to go ahead and peer with router 1. Okay, so additionally here, we'll say no BGP default IPv4 unicast. That's going to apply to our new neighbor. So we're going to neighbor with router 1. From our loopback, update source loopback 0. And then activate them under the VPN v4 address family. Okay, so if we go over to router 1 now, we want to look at the show IP BGP VPN all summary output and make sure that we've established the BGP connections with router 3 and router 6 and that we are exchanging that particular address family. So if we show IP BGP VPN v4 all summary, okay, we have the peering up with router 3. And we can also see the pairing with router 6 is up there. Now, when we look at this output, we can see that even though we have established VPN v4 connectivity with them with multi-protocol BGP, we are not learning any updates from them. Okay, the reason why, router 1 does not have any VRFs locally configured here. So when it is receiving these updates, it's looking at the route target, and it sees that it does not match any import route target policy that is set up on router 1. Okay, so what we're going to do, we're going to create a VRF here. We're going to put a new interface in this VRF, and that's going to act as the central services. Okay, so on router 1, we'll say IPVRF VPN CS, we'll call this. And we'll give it a unique route distinguisher, so we'll say this is based on our loopback address. We'll say 150.1.1.1, we'll say this is the third VPN. Okay, now we need to figure out what we are going to import. Assuming that the host is going to need a route back to the other VPNs, we're going to need to import both of the route targets from VPN B and from VPN A. So we'll say we want to import 101, and we want to import 102. Okay, so we'll create a new loopback interface. We'll say IPVRF forwarding VPN CS. We'll say our IP address is 10.1.1.1/32. And now when we look at the show IP BGP VPN v4 all summary output, we can see that router 1 is learning updates from router 3 and from router 6. Okay, previously it showed 0 here, but now we can see we're receiving these updates. Okay, the reason why is we configured the import policy to import 101. This is the route target used in VPN A, and we're importing 102. This is the route target used in VPN B. Okay, so if we look at the BGP table here, we say show IP BGP VPN v4 all. You can see we have a couple different route distinguishers in the network. We have stuff that is coming from router 3 for VPN B. We have stuff that is coming from router 3 in VPN A. Then we have routes coming from router 6 in VPN A and from 6 in VPN B. Okay, the reason, or the way that we can tell this is based on the way we set up the route distinguisher policy. We knew VPN A was the first instance, and this is the router ID of the originating router. So these are coming from router 6, this is for VPN A. These are coming from router 6, this is for VPN B. Now, we could have used the same route distinguisher for VPN A on both router 3 and router 6, but then when we're doing our verification and troubleshooting, it makes it a little bit more complicated to see where the updates are coming from. But by quickly looking at the route distinguisher, we can see where they're coming from and which particular VPN that they are related to. Okay, so the next thing that we're going to do is advertise this new prefix, this new loopback, into the BGP process. Okay, we could do this by redistributing connected, or we could simply issue the network statement under the BGP process. So what we're going to do under BGP, we'll say address family for the VRF VPN CS. We're going to advertise the network 10.1.1.1/32 with a mask of /32. Additionally, we need to determine what is the route target we're going to use as we are advertising this into the BGP process. You know, we have a couple different options here. We can reuse the route targets that are already in the other VPNs, so we could export them as 101 and 102. This would automatically cause VPN A to import the policy, or to import these prefixes, and also for VPN B to import them. Okay, another option, we could choose a new route target that is going to be specific to this VPN CS. And then on the specific sites that we want to advertise this in, we can go ahead and import that in as well. Okay, the second option is going to give you more control over which specific sites it is allowed to go into. So if we define a new route target here, we can say that we want the VPN site A attached to router 7 to have the route, but we don't want the VPN site A attached to backbone 1 to have the route. Okay, so we'll look at it doing both fashions. First, we'll start off using the route target we already have, then we'll define a new one. Okay, so under IPVRF VPN CS, we'll say we want to export this as 101, and we're going to export it as 102. So two separate communities are going to be on this individual prefix. Okay, we can verify this by saying show IPBGP VPN v4 10.1.1.1. Okay, this will be in all tables. And we can see that it is installed in the BGP table. We see 150.1.1.1:3, that is our route distinguisher. Now if we go to the other end of the links, if we go to router 3 and show IP, we'll do the same thing, show IPBGP VPN v4 all 10.1.1.1. Okay, as of yet, we do not have it installed. Okay, so let's double check the peering here first. We'll say show IPBGP VPN all summary. Okay, we are receiving the prefix, so it should be installed now. Let's see. Okay, we can see we're learning it from router 1. It has two route targets associated with it, 100:1 and 100:2. Now, if we look at our import policy here, we can see, actually, let me include import or VRF. Okay, we can see for VRF VPN-A, we're importing 101. Okay, since this route target is assigned to the prefix, that is going to go into the VPN-A routing table. Okay, we also are importing 100:2. That is also assigned to the prefix, so now it's going to go into the VPN-B routing table as well. So if we say show IP route VRF VPN-A, and we'll include just 10.1.1.1, we can see that is installed via router 1. And if we look at VPN-B, we can see it's also installed. Okay, so it's installed in both VRF tables. But if we look at the complete output here, let's say show IP route VRF VPN-A, and show IP route VRF VPN-B, we can see, for example, that the routes in VPN-B, which are the 31 networks, these are not being leaked out into VPN-A. A VPN-A does not have those 30 or 31 networks. So what we did setting up this central service export on router 1, it does not affect the other filtering policies that are set up anywhere through the network. Okay, so what we should see here is that if we go to router 7, for example, and we show IP route 10.1.1.1, we see we have reachability to that, or we have a route to it at least. Okay, if we look at router 8, show IP route 10.1.1.1, we also see that prefix. Okay, everyone that is in VPN-A and everyone that is in VPN-B, they should now have a route to this prefix. Okay, let's go ahead and see if we have connectivity. Okay, we have connectivity from router 8. And we have connectivity from router 7. Okay, if we take a look at the backbone devices, if we go to backbone 1, show IP route RIP, we see we have a route to that destination, 10.1.1.1. And if we look at backbone 3, show IP route VRF BB3.1. Okay, we see that we also have that installed. So by exporting the prefix on router 1 with the route targets that the other VPNs were already importing, we're allowing it to move between the different VRF tables. Okay, so it's the route target that ultimately controls where the prefixes are going to be. Technically, these are separate VPNs, but we're leaking traffic between them based on the route target filtering. Okay, so if we look at our configuration on router 1 again, we can see that it's importing routes in 101 and 102. Okay, those are routes that are coming from VPN A and from VPN B. And as we are advertising routes from the VRF into BGP, we're tagging it with both 101 and 102. Since these are already configured as import route targets on both router 3 and router 6, no additional configuration is necessary there in order for them to get reachability to that prefix 10.1.1.1. Okay, now the disadvantage of using this method here, exporting with the route targets that the other VPNs are already importing, is that we don't have control over which specific sites the prefix is going to be advertised to. Okay, so what we could say instead, we're going to create a new route target that specifically relates to this central services VPN. If we have customers that need access to this, we will just go ahead and add that to their import policy under the VRF. Because we can see here we can have multiple imports and we can have multiple exports. Okay, so let's go under the VRF here on router 1. VPN CS. We'll take these export policies off. And instead, we're going to export with a new target. We'll say it's 103. Now let's say, for example, that we want router 7 and router 8 to have reachability to this new network 10.1.1.1, but we do not want backbone 1 or backbone 3 to have reachability to it. So what we need to do is simply on the individual PEs inside their VRFs, whatever VRF we want to advertise this to, we're going to configure a new import policy to import 100:3. Okay, so if we go back to router 7 now, for example, we see we do not have connectivity to that destination anymore. It actually should not even have the route for it installed. Okay, likewise on router 8, if we show IP route 10.1.1.1, we don't have a route to this. Okay, because the route target changed, and now router 3 and 6 are filtering it out based on that default route target filtering. So let's go ahead over to router 3 and router 6, and we're going to go ahead and import routes that have a route target of 100:3. Okay, so let's go ahead and look at this on the diagram first. Okay, so what's happening on router 1, we're taking this VPN CS and we are exporting it into the BGP domain with the route target 100:3. Now on router 3 into VPN A, we are importing 100:1. On router 6 in VPN A, we're doing the same thing. We're importing 100:1. And on VPN B, we're importing 102. And same on router 3. Now, if we want only router 7 and router 8 to have reachability to this VPN CS, what we're going to do is that on router 3 in VPN A, we're additionally going to import 103. And on VPN B on router 6, we're going to add 103. But on router 6 under VRF VPN B, we'll use just 101. And likewise on VPN B for router 3, we're going to use just 102. Okay, so if we go to router 3 here, and if we look at the show IP BGP VPN v4 all summary output, we can see it says we are not learning anything from router 1. Okay, the reason we're not learning anything from router 1 is because we are, by default, filtering out the route targets that we do not have import policies configured for. So we're learning that prefix with the route target 103. Since we're not importing that, we're telling router 1 not to advertise that to us. Okay, so if we go to the VRF VPN A here, what we're going to do is say we're going to import 100:3. We can see now when we look at the summary output, we can see we are receiving that prefix now from router 1. Because once we add the new import policy, router 3 is asking for a triggered update from its VPN neighbors, and it's going to resort through whatever route targets they are advertising. So if we say here on router 3, show IP route VRF VPN A, include 10.1.1.1, we can see it's installed. But if we look at VPN B, it's not installed because route target 100:3 is not being imported into that particular VRF. Okay, so it is locally significant on the PE router which route targets are being imported into the VRF. So when we go over to router 6 here, and we say IPVRF VPN B, we want to import 103. This is not going to affect the VPN B site on router 3. So if we look on router 6, if we say show IP BGP VPN v4 all summary, we can see we are learning that update from router 1. And if we look at the show IP route VRF VPN A output for 10.1.1.1, we don't have that route installed. But for VPN B, we do. Okay, so if we look at the backbone routers, if we go over to backbone 3, show IP route RIP, we do not have 10.1.1.1/32 installed. If we go over to backbone 1, show IP route RIP, we don't see that installed. But router 7 and router 8 should. And we can see that both router 7 and router 8 have connectivity to that prefix. Now, if we look at router 1 here and say show IP route VRF VPN CS, we can see that there's actually a lot of unnecessary information we have here installed in the routing table. because even though we have the routes to the 212 network, they do not have routes back to us. So if we wanted to implement a more granular filtering policy, what we could do is on the individual sites, on the VPN-B site of router 6 and router 3, we could use separate export route targets and keep track of which individual targets that we want to import. Okay, so if we use a separate route target export on every individual PE, we're going to control exactly which specific sites that we can talk to. So for example, let's take a look back at the diagram here. If we wanted to optimize this so only router 1, or router 1 only has the routes to router 7 and router 8, we would need to change what the export policies are on router 3 and router 6. Okay, there's a question here. Since the VRF is case sensitive, should we use uppercase? Personally, I would recommend anything that is a user option in the iOS. Personally, I use uppercase for all of that stuff. Okay, so anything that's case sensitive in iOS, I use uppercase. The reason why is that when you're sorting through the configuration file, when you're looking at the show run output, you can see anything in uppercase is going to be something entered by you. Okay, all of the syntax, all of the commands that are built into the iOS, all of those are going to be in lowercase. So whenever I create a route map name or a named access list or a prefix list, I always use uppercase. It makes it a little bit easier when you're sorting through to see what is something that you are defining, so what is a variable you're defining in iOS versus some keyword that is already there. Okay, so if we wanted to make this policy a little more granular, what we could do is that on router 3, we'll say when we are exporting routes from backbone 3 into the VPN network, we're going to send these as 100. Actually, we'll use the router IDs. Okay, this will make it a little more granular. So we're going to say we'll send these as 150.1.3.3 colon 3. And as routes are coming from router 7, and we send those in, we'll send them as 150.1.3.3 colon 7. Then on router 6, as they're coming from router 8, we'll set them as 150.1.66 colon 8. And as they come from backbone 1, we'll send them to be 150.1.6.6 colon 8. Okay, now in order to keep track of this in the CCI lab exam, you're going to have to use some method. Because if you have to constantly go back between the router's configuration and look at what the export policies are and what the import policies are, it can get very complicated as you start to add a lot of VPNs to the network. So personally, what I would recommend is write down on paper what router you have, what VPN it has, and what are the specific route target exports and what are the import policies. So if you look at this sheet of paper that's listing what all the export and import policies are for the different VRFs, you can quickly see which VPNs should have connectivity to each other. Because ultimately the routing information filtering is going to be based on this export target and import target policy. Okay, so let's go back to the command line here. Okay, so there's a question here. Is it router 3 telling router 1 not to send those routes, or is it router 3 filtering the advertisements and not accepting them due to the import policy? Okay, we can actually tell this based on the debug BGP output, and it's going to tell us what we're doing once we receive those route targets. So once we set up this new policy, we'll look at some debugs in the BGP output, and we'll see what happens once it receives those individual route targets. Okay, so first thing we're going to do, we're going to get rid of all the imports and exports on router 3 and router 6. Let's say show run include IPv4 VRF, VPN, or route target. Okay, so we'll get rid of all of these import and export policies. So we'll say on IPVRF VPN A, get rid of those imports and exports. And same with VPN B. Okay, there's a question here, can I use 1:X for router 1, 2:X for router 2, etc. for the route distinguisher? If they don't tell you what route distinguisher to use, then you can use whatever you want. Okay, it should be at least unique on a per VPN basis. It should be. It doesn't necessarily have to be, in the case where it wouldn't make a difference if your customers were not using overlapping address space. Okay, it's really only going to be an issue when they're using overlapping address space, because the route distinguisher is going to make those same prefixes be unique by adding the distinguisher onto them. Okay, so if they are not telling you what policy to use, then I would make it unique on a per VPN and per PE basis. So whether you use the IP addressing format or whether you use the AS number format, I would personally make it unique on both the VPN and the per PE basis. So then when you're trying to do your troubleshooting, you know exactly what VPN this belongs to and what router was originating it into the domain. Because depending on how the design is, you can see that sometimes you'll see multiple routers are exporting the same prefix into the network. So for example, if your customer site is dual homed, if both of the provider edge routers are using the same route descriptor or route distinguisher, when they export the routes in to BGP, you're going to have trouble figuring out, did it come from the first provider edge router or did it come from the second provider edge router? Since they're both using the same route distinguisher and it's the same prefix, then it's going to be kind of hard to tell with your troubleshooting process. But if router 1 uses this specific route distinguisher and router 2 uses a different one for that VPN, then you'll quickly be able to see which PE router that you're learning that particular prefix from. Okay, so on VPN A here, we'll say IPVRF VPN A, we are going to export our prefixes. We'll use our router ID. We'll say 150.1.3.3, :1. And for VPN B, we'll say 150.1.3.3, :2. Okay, then on router 6, we'll do the same thing. So we're going to export these, say route target export. We'll export as 150.1.6.6, :1 for VPN A. Then for VPN B, we're going to export 150.1.6.6, :2. Okay, so not only are we using a unique route distinguisher per PE per VPN, we're also using a specific route target per PE per VPN. Okay, so this is going to give us a little bit more control over is going to give us more control over what specific sites have access to the other sites. Okay, now at this point, if we look at the show IP-BGP VPN before all summary output, we're going to see that we are not learning prefixes from router 1, and we're not learning prefixes from router 3. This is based on that default route targeting or route target filtering that is enabled for the VPN v4 address family. And now, if we look, let's go ahead and look at our debug output here. Let's say show debug. We'll undebug MPLS packets. We'll debug IP-BGP VPN v4 unicast import processing and updates. Okay, then we'll go ahead and clear, let's go ahead and clear the BGP process. So first off, we'll clear the log, then clear IP-BGP asterisk. Okay, then once these neighbors come back up, then we'll take a look at what the debug output we have in the log is. So let's say show IP-BGP VPN v4 all summary. Okay, they're back up now, so let's say show log. Okay, so what we can see first off, from router 3, we are receiving routes. We're receiving 150.133:2 31.300/16. It says denied due to extended community not supported. The extended community not supported, it's telling us that we do not have this route target set as an import route target policy. If we had whatever the extended community was, we can't actually see the community here. They're just showing us that is the prefix. Okay, but if we supported the community, then we would go ahead and install it in the table. Now, if we go ahead and add the community in, this is going to be under VPN-B because we see it's 150.133:2. So if we say, we'll go to global config, IPVRF VPN-B, and we want to import the routes coming from router 3 that relate to VPN-B. If we look at the log now, okay, let's make sure that's importing it properly. Let's say show run. I have it in here still. Show run include the VRF or the route targets. Okay, so for VPN-B, we're importing the routes that are coming from router 3. So actually, let me turn logging to the console back on here. It's still saying they're denying these due to extended community not supported. 150.1.3.3:2. These should not be denied. Let's see. Show IP-BGP VPN v4 VRF VPN-B. Okay, so we have only those routes in. Sometimes you'll see that the route refresh capability doesn't work with this, and that you need to do a hard BGP clear. That's probably what's going to happen in this case, because we can see router 3 is sending them to us as 150.1.3.3:2. Okay, that's the export route target that router 3 is using. We are importing that. We are importing 150.1.3.3:2. Let's double check on router 3 to make sure that we are actually exporting them as that route target. Route target export 150.1.3.3:2. Okay, so router 6 is importing the route target value that router 3 is exporting. That's the correct config. So really router 6 should be accepting these prefixes, but it's not. So let's go ahead and try clearing. We'll just clear the whole neighbor. Clear IPBGP 150.1.3.3. So it's receiving them, it's still denying them. Let's take a look at the VRF table. Let me try clearing it on router 3. Okay, let's go on router 3. Let's try to import the routes that router 6 are sending. Let's see. Okay, now it's receiving them. Okay, so it just took a while to update it. So we can see they're denying the ones. This is why you don't want to debug this stuff to the console. Stuff like BGP debugs, things that are really going to be useful for your troubleshooting, they're typically very noisy debugs. So you ideally don't want to send this stuff to the console. Send it to the buffer so you don't accidentally lock yourself out of the console. Okay, so it says that now we're installing these from router 3 into the VPN table. So what happens first off is that router 3 is advertising the routes. A6 is sending the message back to router 3 that I'm denying these based on the route targets. Router 3 is not going to re-advertise those again unless 6 requests route refresh from them. So router 3 is sending them first off, but then they get filtered out by router 6, and router 3 doesn't send them again. So let's go ahead and take a look at the VPN table on router 6 here. So we'll say show IPBGP VPN v4 VRF VPN B. Okay, so we can see the routes from router 3. Those are getting installed in the table now. If we go over to router 3, we'll go ahead and under IPVRF VPN B, we'll say we want to import the routes that router 6 is advertising for VPN B, and under VPN A, we want to import the ones that are coming from router 6 as well. Router 6 is going to need to do this for both VPNs as well. So for VPN A, we want to import 151.3.3:1, and for VPN B, we're going to import 151.3.3:2. Okay, now as you can imagine, this is a pretty simple case because we only have 2 provider edge routers that we're dealing with. But as the size of the VPN table gets larger and as the number of PE devices get larger, it can get pretty complicated to figure out who is importing which specific site's routes. So like I said, make sure that in the lab exam you're keeping track of this some way, because if you spend an hour just looking back and forth between configs to figure out who is exporting what and who is importing what, that's going to be a lot of unnecessary wasted time that you have in there. Okay, so at this point, we should have connectivity between the regular VPN A and VPN B sites. So let's go to the customer routers, router 7 and router 8, and we'll look at their routing tables. Show IP route rep. Okay, router 7 has reachability to backbone 1, or at least it has the route. So let's see if it has reachability. Okay, so we have reachability there. And then on router 8, show IP route rip. Okay, we have the routes installed. Let's ping 30.0.0.1. We'll source it from 10.1.8.8. Okay, we have connectivity there as well. Okay, so let's take a look at the VRF policy we have here. So we can see for VPN A, we are exporting 150.1.6.6:1. This should be the value that router 3 is importing for this VRF. Likewise, router 3 is exporting 150.1.3.3:1. This is why router 6 is importing this value. Okay, then vice versa on VPN B. We're exporting this. This is what router 3 should be importing. And we are importing what router 3 is exporting. Okay, now if we look at the central services configuration on router 1, and we show IP route, VRF, VPN CS, okay, we see that we don't have anything installed except for that connected loopback. Okay, the reason why we are not importing the correct prefixes from those other neighbors. Okay, so if we look at our policy here on router 1, we're still importing those old values. So what we can do now is for this VRF, we're going to import these new values. So we'll say we want to import 150.1.3.3:1, and we want to import 150.1.6.6:2. Okay, so these are the routes coming from router 7. These are the routes coming from router 8. So when we look in our table, show IP route VPN or VRF VPN CS, we see the routes from router 7, we see the routes from router 8, and we see those two transit links between them. Okay, so we don't see any of the routes from backbone 1, and we don't see any of the routes from backbone 3. Okay, this is only the import policy that we affected on router 1. What we still need to do is go to router 3 and router 6 and configure them to import what router 1 is exporting. Okay, so if router 1 is exporting 100:3, but the other ones are not importing it, we can see if we ping inside VRF VPN CS, we ping 10.1.7.7, we don't have connectivity there because that VRF does not have our routes. Likewise, router 8, it does not have our routes. But if we go to router 3 here in under IPVRF VPN A, we are going to import 103. And on router 6, under VRF VPN B, we're also going to import 103. Okay, so we can see that router 1 has connectivity to router 7 and router 8. None of the backbone devices, so if we go to backbone 1 or backbone 3, go IP route RIP, okay, they do not have a route to the 10.1.1.1 network. That's because on those specific PE routers on router 3 and router 6, we are not importing that route target into that specific VRF instance. Okay, they only have the routes to their regular VPN. Okay, any questions on this central services design with using the different import policies and export policies? Okay, the next case we're going to look at is a management VPN example. Let's say that router 5 is now also a provider edge router, and we have a management station that's located on router 5. We want this management station to be able to telnet to router 7 and to router 8, but not have access to any other prefixes within the customer. Okay, they're going to be using this management station just for collecting SNMP traps or doing Armon, that type of stuff. Maybe router 5 is an NTP server that they're getting time from. So what we're going to do is on router 7 and router 8, we're going to configure a new management loopback. And when we export this from the VRF into BGP, we're going to do it selectively based on a prefix list. So we're going to say if this prefix list, or if this prefix is received from the customer, we're going to go ahead and export it with a particular route target. And then router 5 is going to be importing those, so they're going to go into that management VPN on router 5. Okay, so the first thing we need to do here is go ahead and establish the BGP peerings with router 5 and 6 and with router 5 and router 3. Okay, so on router 5, we'll go ahead and run BGP. Okay, we'll run BGP, and then we're going to peer with, actually first off we'll say no BGP default IPv4 unicast. Okay, because we're running just VPN here. So we're going to peer with router 3, and we're going to peer with router 6. Okay, both of these, they're coming from our loopback interfaces. Then both of these, under the address family VPN v4, we're going to activate them. Okay, so we'll have our new management loopback on router 5. We'll say loopback 1. This is 10.1.5.5/32. Actually, let's say 100. Okay, new major network, 100.1.5.5. You know, on this particular loopback, we're going to go ahead and put it into a new VRF, and that is going to be exported with a route target that both router 3 and router 6 are going to send into that management or into those VPNs. So they're going to go into VPN A on router 3, and it's going to go into VPN B on router 6. Okay, so we'll create the VRF. We'll say IP VRF VPN management, MGMT. We'll say that as we export it, we're going to export it as 150.1.5.5:100. Okay, so some new unique value. Okay, this has a route distinguisher. We'll use the same, 151.55:100. Okay, we are going to import two separate values that are going to be used on router 3 and router 6. We'll say that these are going to be, this new import policy is going to say router 3 is using 150.1.3.3:100, and router 6 is going to use 150.1.6.6:100. Okay, then on this loopback interface, loopback 1, IPVRF forwarding VPN management. Okay, then we'll go ahead and peer with router 5 on router 3 and router 6 via VPN. Okay, so under the BGP process, we'll say neighbor 151.55, remote AS 100. Under address family VPN v4, we'll go ahead and activate the neighbor. Okay, same configuration on router 6. Okay, now inside our two VPNs there, we'll have IPVRF VPN B. We are going to import what router 5 was exporting, so 150.1.5.5:100. And we'll do the same thing on router 3. So on our VPN A, we're going to import what router 5 is exporting. Okay, there's a question here. Can you use the show IPBGP neighbor received route output or option? You can, but it depends on the legacy route refresh, or the, no, excuse me, not route refresh, soft reconfiguration. Okay, so you would have to say for this specific neighbor, allow soft reconfiguration inbound, and that typically is replaced by the new route refresh capability. Okay, so if you wanted to, you could go ahead and enable soft reconfiguration and then see what is the difference between what you're receiving and installing. But generally, in an SP environment, you don't want to do that because it causes extra memory utilization. So what would actually happen if you did that is that you would have a full VPN table with every single route from all the other provider edge routers. Okay, and what the VPN route target filtering does is trying to prevent that case. So it's trying to prevent you from having to install every single VPN route in your network. It's only making you install the routes that you're actually going to use based on your VRFs. Okay, so you could do it, but design-wise, it's really not a good idea to go ahead and do that. Okay, so if we take a look on router 3, let's say, actually we didn't advertise the network on router 5, I believe. So under BGP, address family, IPv4, VRF, VPN management, we're going to advertise 100.155. Okay, we can see on router 3 now we have reachability to 100.1.5.5. It's coming from router 5. The route target is 150.1.5.5:100. And if we look on router 6, we should be able to see that as well. Show IPBGP VPN all 150 or 100.155. Okay, so we do see we have that installed. Okay, so the management station is on router 5. We're advertising that into BGP. We're making sure that router 3 and router 6, which are the provider edge for router 7 and router 8, they have that route installed. Okay, that's being redistributed into RIP, and it's going to those customer edge routers. So if we look at router 7, show IP route 100.155, we see that we do have the route to it. Okay, if we look on router 8, we should see the same thing. Show IP route 100.155, we do have that route installed. Okay, now what we're going to do is create 2 new interfaces on router 7 and 8. And when we export those on the provider edge routers, we're going to do it selectively based on those specific IP addresses. So we're saying as we're learning these IP addresses from the customers, when we export them into the multi-protocol BGP network, we're going to assign a different route target than all of the other prefixes. Okay, so first off, we'll go ahead and create these. So we'll say interface loopback 1, IP address 101.88/32. Okay, under RIP, we'll say network 100. Same thing on router 7. IP address 101.77/32. And then we'll advertise it into RIP. Okay, if we look at router 3 and say show IP route, VRF VPN A 101.77. We should have that route. Okay, we do have it installed as a RIP route. On router 6, we should see show IP route VRF VPN B 101.88. Okay, we see all of those installed. Now, right now, the way it sits, these are being exported into BGP with the normal route targets that are listed under our policy. So if we show run include IPVRF VPN or route target, for VPN-B here, these are being exported with 2 different values. Or no, they're being exported as 150.166:2. Okay, what we're going to do is change this, so this specific prefix on router 3, and then the specific prefix on router 6, they are exported with different targets. Okay, we're going to use a prefix list and a route map to accomplish this. Okay, first step, we need to match the prefix. So we'll say IP prefix list R7 management for bit 100.1.7.7/32. Okay, so you should already be comfortable with prefix lists and access lists. We're not going to spend a whole lot of time going over these options in the command line. Okay, so we're matching the prefix. Now we're going to create a route map that will say export router 7 management. Match IP address, prefix list, R7 management. Now under this VRF, IPVRF VPN-A, we're going to apply a specific export map. Export map, export router 7 management. Actually, before we apply that, we need to, in this sequence, mid 10, we need to say set BGP we need to set the BGP extended community to this specific route target. Okay, route target value here is going to be 150.1.33 or 150.1.3.3:100. Okay, then under the VRF, we'll say export map, then the map name. Okay, so here on router 3, we have two different types of exporting that are happening. We have the specific export map, which is matching an individual prefix. Then we have the global export. Okay, so if we go to the other routers, let's say we go over to router 6, and we say show IPBGP VPN before all. Let's see what we are learning from router 3. Okay, we still have the this stuff coming from router 7. We have 101.77/32. That may be in the process of converging right now. Let's say show IPBGP VPN all 100.1.7.7. It says the route target is 150.1.3.3:1. Okay, let's go ahead and we'll say clear IPBGP VPN unicast 100 inbound. Okay, that's going to ask router 3 for route refresh. Okay, let's try clearing this outbound on router 3. Clear IPBGP VPN unicast 100 outbound. Okay, it still has that same target. Let's take a look on router 5 and see if router 5 is learning it. Show IPBGP VPN all summary. Okay, so it's not learning anything from router 3. Let's go ahead and on router 3, we'll just do a clear IPBGP asterisk. So we'll do a hard reset of both router 5 and router 6's session. Okay, we can see now on router 5, we are learning the prefix from router 3. So let's look in the VPN table. We'll say show IPBGP VPN all. We see we have 101.77. So let's say show IP VPN, show IPBGP VPN, and then this specific prefix in all. Okay, now when we look at the route target, we can see that it only has the route target 150.1.3.3:100. So it did not inherit a global export target that was configured under the VRF. Okay, so it was only assigned that specific one that was in the route map. Okay, now you can use multiple set statements because you can tag multiple extended communities onto the BGP update. So we could have set multiple route targets if we wanted to. Okay, now if we look at router 6 and show IPBGP VPN all, that prefix, we don't have that in the table because router 6 is not importing 150.1.3.3:100. Okay, but if we look at the other prefixes that are coming from router 3, we should still see the other prefixes, which we do. Okay, these have a community, the route target community, let's say show that route, we'll say show 10.170. Okay, this prefix has a route target of only 150.1.3.3:1. Okay, so it's not inheriting both of them. If you want to do both of them, then in the route map, you would have to specifically have multiple set statements. Okay, so if we do the same thing on router 6, we'll say IP prefix list. This is going to be router 8's management loopback. Permit 101.88/32. Okay, our route map, which is going to be export router 8's management loopback. We'll say match IP address prefix list R8 management. Then under the VRF, IP VRF VPNB, we're going to export using, actually I forgot to set it. Okay, so we already matched it. Now we're going to say set extended community to the route target 150.166.100. Okay, then under the VRF, we're going to go ahead and export this. So we'll say export map, export router 8's management loopback. Okay, so if we look on router 5 now, in the BGP table, show IP BGP VPN all, we see 3 different prefixes. We see our own local loopback, then we see the 2 loopbacks from router 7 and router 8. Okay, so the management station here, when it sends traffic to router 5 is only going to have routes to the individual CE devices. So we could, for example, telnet to 101.77. We'll source it from 101.55. Let me try the VRF first. VRF VPN management. Source interface is 101.55. Or source interface loopback 1. Okay, so we don't have reachability here. Let's make sure we do have the routes here. Show IP route VRF VPN management. Actually, no, we don't. Okay, sometimes you can see inconsistencies like this. We have them installed in the BGP table. We can see this from the show IP BGP VPN output. They are installed in the VPN table. They are best routes in BGP, but they're not being installed in the VRF table. Okay, when you see this, typically what's going to work if we say clear IP route VRF VPN management and clear all the routes in there. And that's not working in this case. Let's try clearing the BGP process. So as you can see, a lot of this stuff is really slow to converge, and if you're not 100% comfortable with what your configuration is, you can end up troubleshooting a problem that doesn't really have anything to do with your configuration. Okay, so you need to get to the point with this where you're really comfortable knowing that you're putting the correct options in there, and if you see that the routes are not getting installed or you don't have connectivity, then you know where to start your troubleshooting process. Okay, so first off, I want to see if I can clear the VRF table, see if the routes are going to move from the BGP table into there. Because we saw we were learning them from the neighbors. They were best routes in BGP, and we knew that we already had a route to those loopback addresses. So if we ping in the global table, if we ping 151.1.1, 33, and 66, we know that we already properly built our IGP network, and we properly built our label switch path to these particular prefixes. So that's not going to be an issue here. So we should see, hopefully, that it's now they're in the routing table. Okay, so clearing the BGP process, reset them, and now they got installed into the BGP or into the VRF table. Okay, but as you can imagine, if you fall back and start troubleshooting your transit network, you're going to be wasting a lot of time when really it has to do with just the slow convergence of the updates. Okay, so now if we go ahead, let's try to telnet. To switch 1 or to router 7, we see we have connectivity there. If we telnet to 101.8.8 inside this management VRF, we can see we can reach it as well. Okay, so in this type of circumstance, we're picking out individual addresses that we want this VRF to have reachability to. Now it doesn't necessarily have to be for the purpose of management. We could have like a file server that we want some VRFs to have access to, but we don't want to give them access to the entire segment. So we could say for that particular prefix, go ahead and export it into the BGP domain with this specific route target that they are going to be importing. Okay, there's a question here. So there's no need for another instance of export router 8's management. All others assume the default route target for the appropriate VRF. Yes, that is true. Now we could set it up in a case where you're not using the global export command at all, and you're doing everything inside the route map. So, for example, on router 6, if we look at its VRF configuration, instead of saying, we could say under VRF VPNB, we'll get rid of our export route target, and we'll say inside route map export router 8 management. We'll say permit 10,000. Then set extended community to route target, whatever that value is. Okay, so if you do something like this, it's a little bit easier to understand when you look at the configuration, because then you don't have a possible conflict of the order of operations. So when you have both of these in here, you're wondering, well, which is going to be chosen? Is it going to be the more specific one, or is it going to be the general route target export? If you do everything inside the route map, you know exactly what's going to happen, and it's based on the top-down processing. So sequence 10 says you're going to set it to this route target. Then our last case sequence 10,000, is setting it to this. So this would be like our default route target, our export route target that's going to be for everything. Okay, so there's a lot of ways to accomplish the same goal here. It just depends on ultimately how much control the service provider wants over what's going on inside its network. So it's going to be a balance between the amount of configuration that's needed and the amount of filtering and flexibility that's needed. Now, if you start your configuration with something like this, it's a lot easier to make it flexible later in your requirements. So if your requirements change where you want reachability between some specific sites, you wouldn't necessarily want to have to go back and re-provision every single VPN that you have based on a new route target export or import policy. But by doing it this way, where each individual VRF is exporting differently on the different provider edge routers, you're going to need more import statements, but it's ultimately going to give you more flexibility in the end, exactly what routes are going to go between what devices. Okay, so there's a number of different examples for this stuff in the Technology Lab series, doing the basic VPNs between the neighbors. We didn't look at using different PE to CE protocols. We'll talk about that a little bit more tomorrow morning, some advanced features with those. But the topics we looked at with the VRF Lite, using the VRF using the VRF-aware protocols, it's going to be the same exact case when you run these between the PE and CE. So if we take a look at that real quick, we saw VRF-aware RIP, how we were running that on the provider edge. Okay, so we had the RIP process, then we were redistributing between RIP and BGP. If we did EDGRP, it would be the exact same thing. Okay, we could run EDGRP with the customer network, then on the customer side, they would just say router EDGRP1. That's the that's the autonomous system number for that particular VRF. Likewise, if we ran OSPF. Okay, OSPF is going to be a little bit more complicated. We'll talk about that tomorrow morning, how you deal with virtual links over the MPLS network, how you deal with backdoor routing with OSPF, and then we'll talk about some more features with using BGP as your PE to CE routing protocol. Okay, so we can say just for this particular VRF, I want that neighbor who is in the VPN to establish adjacency with them. Okay, and this is relating to IP version 4 unicast you're exchanging with them. There's a question here, would multi-VRF IGP work between the customer edge and the provider edge? And the answer is yes. Okay, you can run into certain designs where, let's say, for example, you have like an office building that the service provider has an edge router in this office building, and it is managing the customer edge device. You may have inside the office building, you may have different businesses that you want to separate them into different VPNs. So what you could do on the customer edge, it doesn't necessarily need to be MPLS aware, but it can be VRF aware. So for example, like on the Catalyst 3550 and 3560 switches, they don't support MPLS per se, but they do support multi-VRF. So you could configure multiple routing tables so the people in Office 1 can't talk to the people in Office 2. Then you can take routes from Office 1 and Office 2, send them upstream to the provider edge. Then the provider edge can grab those routes through your VRF interfaces and then send them into the MPLS network. So that's traditionally what you see when you look at the design of multi-VRF or VRF Lite, which is when you have a managed customer edge device. And like you said here, this would allow for overlapping prefixes within the same network. So if you had those different offices in that office building, they could be using the same addressing space. Okay, so they could all be using the 192.168.0.0 addresses, because the customer edge device, if it's running multi-VRF, it's treating those as separate prefixes based on the route distinguisher. Okay, any questions related to the import and export policies of the VRFs that we just talked about? Okay, you'll see when you're looking through a lot of different resources for MPLS, they get kind of crazy with the terms that they're using for these, the different hub and spoke, full mesh, central services, management VPNs. You'll see a lot of different terms for this. But basically, all these complex VPN topologies boil down to what is your import policy and what is your export policy for your route targets. So if you have a full mesh, it just means that whatever I'm exporting, everyone else in my VPN is importing that. If I'm hub and spoke, I'm saying some of the routers are importing everything. Some of them are importing just a subset. Same with central services. We're exporting a well-known route target, and then other people that want access to it, they're importing that. Okay, we'll also talk about later in the week some advanced features with the VRF select option, which allows you to put a specific host into a different VRF. So we could say we have an Ethernet segment that has 2 different web servers on it. We could say server 1 is in VRF 1 and server 2 is in VRF 2. And that's going to be based on the VRF select feature that's available on the 7200s. Okay, so let's go ahead. Let's go ahead and take about a 15-minute break. We'll start back at about 15 minutes after, and then Brian Dennis is going to cover MPLS traffic engineering, and then that will bring us up to the end of the day. Okay, we'll start back. So we'll start back in about 15 minutes.